So thank you for that introduction. So thanks to our mentors. So I'm Alex, this is Niall, Swain, and as was mentioned, we're all late students. And yeah, this is our project. So just to reiterate, the kind of brief is essentially to simplify polygons what we're taking coverage. So we want a shape with less points that covers the original shape. Ideally, we want this shape to be as close as possible to the original shape. So just to kind of set the problem boundaries, you start with something like this, which has many vertices. Obviously, it's going to be more complicated. This is complicated in this case. And we want to get something in the middle, which has less vertices, still kind of approximates the shape, but is simpler. If we go too far, then we get to the convex hull. That's kind of the baseline of our problem, because that's the simplest possible shape that covers our original shape. And now we'll talk a bit more about that later. So what are our primary results? We created a package that's on GitHub. It has a Python API for line simplification, which makes it quite easy to use. We implemented 3 different line algorithms that simplify these polygons depending on your heat. And we also, for at least one of the algorithms, added adaptive selection of the optimal number of vertices, such that you remove as many vertices as possible while retaining as much coverage as possible. The Rust backend guarantees speed and scalability. We especially added parallelization to make sure it's very quick. And again, we have guarantees on coverage of these polygons.
So this is just to show the comparison between our software and the off-the-shelf Python packages that are out there. So as you can see, the first two is what we have achieved, and it can be from 5 to 10 times faster than what you can with typical off-the-shelf packages, which is very good news. And yeah, so these are the bind reduction algorithms that we have. First is the Wisligen White, and it's an algorithm that minimizes error loss, and it is the one that is adaptive that now we'll talk about later on. The second one is the Gauss-Perker. It is a recursive algorithm, and it preserves different features compared to Wisligen, which we'll introduce itself. And the final one is our experimental chart-shaped algorithm. And it works quite differently, and it can be quicker in certain scenarios. And thanks.
So before we explain the 3 different algorithms in a bit more detail, I just want to do some basic definitions. Kind of three sets, but the convex hull is the smallest convex shape, which covers a set of points. So we have just a generic shape here, and surrounding it's the convex hull. And as kind of said before, we're interested in this because it's the minimal reduction that you're able to achieve. So we're never adding any points, we're only ever removing points. And because we have to cover the original shape, we always end up at the convex hull as the very minimum. But this is quite useful because you can actually, once you compute the convex hull, you can split it into concave segments like this. And then all of these can then be reduced using our line reduction algorithms all in parallel. So that gives us a bit of a performance boost over alternative methods. So with the standard Wisligen-White algorithm, it starts by assigning scores to every single point based on the area of the triangle it makes with its 2 neighboring vertices. So if you picked, say, this point here, I'll do it so everyone can see online, and you would create the triangle with the 2 adjacent ones, and then the area of that is the score. So the idea is with a very, if you had a section that was very flat, so say down here, you could assign a low score to this point, so it's very easy to remove. It wouldn't affect the shape as much. So then we go through sequentially and remove points from lowest to highest score, and that's kind of the general idea. So you can see it in action here. We just picked a generic shape. You can see how it progresses. So it has like a smoothing effect. So over time, it will smooth out the reckless. But this is the original algorithm. So currently, it doesn't do the area coverage that we need. So remember, our reduced polygon always has to be larger than the original. So we need to make some additional changes. And the first is that we can't, so to ensure coverage, when we remove a point, the one condition we need to apply is that the area is always increasing. So in the original algorithm, which is on the right, I was just pointing at, and then on the left is the modified, so our version. You can see in some cases the original will remove a point that intersects with the original shape, and this isn't allowed in our case. The second thing that can sometimes occur is that self-intersections happen. So by removing a point, you can end up creating a non-valid geometry. So you have to do tests for this, and we use an R tree.
So with this random, because you have this like very nice monotonic relationship between the area of the triangles removed and the number of points removed, which you can see here. So on the x-axis, we have the maximal until now area of triangle removed, and on the y-axis, we have the number of like points removed. And we can kind of see that this creates a very nice exponential-ish type curve. And our goal with adaptive selection was to choose a point at the maximum curvature of this curve. So there's something that already exists for this. It's called the Neal algorithm, and essentially it tries to find this point of maximum curvature. It's quite simple. You try to rescale the x-axis and y-axis to be of approximately the same order. You then rotate this curve by 45 degrees by subtracting the x-axis from the y-axis. This, in some sense, reveals that point of maximum curvature, because now, before that point, we can see that the curve is increasing, and after it, it is decreasing. So that's quite easy to, as a criteria to search for. Of course, by itself, it is still a very, very noisy curve. So if we zoom in on it a lot more, we can see that even after smoothing with the Gaussian infernal, it's going to create like this quite rough shape. So we can't just naively search for a point that's larger than its predecessor but smaller than its successor. Instead, we use a window that's kind of probabilistic, and we just take the ratio of points that are increasing to the ratio of points that are decreasing. And we can see that if we zoom in on the peak and take a look at this difference data, over time, as we go away from the peak, there's more and more points that are smaller than their previous points. So, as you go further, the probability that all these points are going to be decreasing is 1. So that's how we adapt it, and that kind of works.
So the second algorithm that we offer is the Douglas-Poiper. And the way it works is that it's easier to explain with the animation on the right. So you define a user tolerance, which you put in your computer. And for the first 2 steps is basically the same as the Wishfang algorithm. You divide the polygon into, using the convex hull to divide it into separate line segments. And you reduce each line segment independently. And but for the second, for this algorithm, the way it works is that for every point, that is the distance between each point and the line that is formed by the points on both ends. If it's bigger than the user tolerance, then you do a recursion and you split the lines and you do everything again. But if it's smaller than this epsilon criteria, then you just remove all the points. But just like the previous algorithm, some modifications needs to be done to fit our use cases. So we've also done some modifications and extensions. The first one is the same as with Wishfang. We check the self-intersections using an R-tree. And one of the big issues with the original VD algorithm is that it tends to overfit. So if you would have removed as much points as we expect it to be. So one of the main improvements is that if you can see on the the first step is that you recurse on this point and you split it into two separate line segments. And if you look at the line segment on the right, although everything is smaller than this epsilon criteria, we deem that there is too many points here that we are keeping. So we split it on the point with the maximum distance again, even though this epsilon criteria is satisfied. So we split it here. And in the end, we have something that is more general and it doesn't have the overfitting problem anymore. So yeah, so here is just a quick comparison with the first and the second algorithm. We compare with same tolerance, and the second scenario is slightly looser. And so scenario number 3 is the first algorithm, which is the Whisper algorithm. As you can see, it might be a bit small, but the river here and some features are not preserved from this algorithm. Whereas for the DP algorithm, you can see that the curve, the red curve here, you preserve this river-like feature and this island here as well. So it really depends on the user's preference and choice of what kind of polygon they want to achieve in the end. And yeah, we also achieve like a similar percentage reduction in points for both of the algorithms.
Our last algorithm is kind of experimental. The previous ones were based on existing line simplification algorithms. This is something we're kind of trying out. It's based on a paper that originally was trying to generate random polygons from point clouds. So essentially agglomeration of points. And you could do the convex hull of these, but it's generally not representative of the actual point cloud. Instead, what you want to find is the characteristic shape of this point cloud, which is this thing. And in practice, it's quite simple. You triangulate your input vertices. You constrain it such that these input vertices must create edges. And then you work backwards from the convex hull and try to get to something that is the shape. And you do this by shaving off exterior edges from this triangulation iteratively from largest to smallest until you get to your target desired number of points. Again, this one is kind of more experimental and we're still tuning it, but it should create different types of futures compared to visible income and RVP. Yeah, so there's some possible extensions to our work that we will probably implement soon. We're experimenting with different loss functions. Currently, we have quite simple metrics. For visible income, it's just a straight-on area. For RDP, it's like this tolerance. What you can, for example, do, though, is penalize, based as a user, certain structures. For example, you take the area, and you also multiply it by some parameter that encodes the sharpness of this like triangle. So if you want to, for example, have a more spiky resulting polygon or a more smooth polygon, you can, using a different loss function, get different results. We also want to add adaptiveness to RDP char shape, where it's not as trivial as with visible income. Also, what would be interesting, it would be multi-scale simplification, where you don't just get one up polygon, but you get a series of upward polygons of multiple resolutions, depending on your specific needs. Finally, also like bend simplifying and bend exaggerated functions are sometimes used in what's called cartographic generalization, where you don't necessarily want the most optimal simplified polygon that minimizes area, but you want something that also has all the geographic features you're interested in, like rivers and so on. And in such cases, you might need to exaggerate the size of that river in the resulting polygon so that it stays there. And these functions would be able to do that. Oh, and finally, we can also relax the brief a bit by adding the possibility of including new points. This would allow for more simplification in some cases.
So just to summarize, our brief was to create a polygon reduction algorithm that always ensures containment. So the original polygon is always contained inside the reduced. We've tried 3 different algorithms, and we've implemented all of these in Rust with a Python-facing interface. And we found very good performance in comparison to existing algorithms. So Shapely is quite a common package fix like this already. And we've managed to beat their performance by a few times. So we're quite pleased with that. As well, the different algorithms can be used in different circumstances. So as Kenneth said, if you want to retain a river or maybe you want to smooth it out completely, these different options are available to you. And then finally, as we said, we currently have the optimal reduction for BizVallingham. So as a user, you don't need to always give it like tuning parameter. It'll kind of self-fit by itself. So I can't promise our example is quite as interesting as the past presentation, but if you want to find out more about our algorithms, you can scan the QR code there. So thank you.
Thank you, guys. Or Ivan, you can keep it. Yeah, you presented like it was like, yeah, I'm gonna do this and that. So, are there any questions? So maybe, have a party using that in the center. How relates that to what we maybe, looking at.
Sorry. Yeah, maybe I can make a comment. So we're planning to use this as a pre-processing steps for, let's say, 2D inputs to reduce the cost of the Polytop server. So it'll basically speed up our, speed up the Polytop server in those cases. Or first, I don't know, you have multiple examples where we could think about extracting, let's say, river catchments, country outlines, things like this. But they're heavily detailed, large number of purchases.
Okay. Questions for the team. I know it's the afternoon and we're on the entire day, but
Does it matter what coordinate system the polygon that you get pat is on? So obviously it could be regular lat long, which would probably be easier, but what if it's something different?
Yeah, it's assumed to be like on a COP-TT grid. We just take a string of points. That's how we draw everything. If you wanted to do it more generally, you might be able to do some projection. And then you do that one.
good. One more question? No? Then another round of applause. So